Now we're going to move on to two concepts that will be helpful in studying sets, and those are Cartesian products and Venn diagrams. First thing we're going to do is define what the Cartesian product of two sets is and show some examples. We're going to describe what Venn diagrams are, and then we're going to show how to use Venn diagrams to understand sets. All right, so I want you to recall from your algebra days the Cartesian plane, and so that just exactly what it sounds like, the x and y axes from the old days when you used to do graphs. So one of the nice things about this setup is that we can identify each point on the plane using an ordered pair of real numbers. So if I put a random point somewhere over there, what I do is I look for the x-coordinate right above or below it and the y-coordinate right across from it, like this. And whatever those numbers are, the one on the x-axis, that's my x-coordinate. The one on the y-axis, that's my y-coordinate. And that tells me exactly where that point is. So if you want to ask what is really happening here from a set perspective, what we're really doing is each axis could be thought of as being a copy of the real numbers. The x-axis contains all real numbers. The y-axis also contains all real numbers. Then each coordinate that we get for points on the plane comes from one of the copies of the set of real numbers. So in other words, we're taking two sets, well, I mean, maybe not two sets, but two copies of one set, and we're making it into a new set using ordered pairs. And we're going to do that with, just in general, with any old sets. So this is called the Cartesian product. So if you have two sets A and B, and they could be the same set, but they could be different as well, then the set A cross B, the Cartesian product of A and B, is the set of all ordered pairs x comma y, where x is contained in A and y is contained in B. So you can think of the elements of A as the items that are allowed to be the x-coordinate. A is kind of like the x-axis, if you want to think of it that way. And the elements of B are the items that can be a y-coordinate. So you can think of B as being the y-axis. So here's an example of two sets, A and B. A contains the numbers 1, 2, and 7. B contains the letters W and X. And let's see if we can write out the elements of A cross B. Well, as you note from the definition, we take an element of A and put that as the x-coordinate, take an element of B and put that as the y-coordinate. Why not try 1, which is in A, as my x-coordinate, W, which is in B, as my y-coordinate. And then I'll keep the 1, but then I'll move over to X as being my y-coordinate. Now I'll move to 2 as my x-coordinate, so I get 2W and 2X. And then I do the same thing with 7, 7W and 7X. And those are all the ways that you can choose an element of A to be the x-coordinate and an element of B to be the y-coordinate. Now, I do want to point out that 1W is one of the ordered pairs in A cross B. But if you turn that around to W1, that is not an A cross B. W is not in A, so it can't be used as an x-coordinate. 1 is not in B, so it can't be used as a y-coordinate. All right, so that's how Cartesian products work. Now I'm going to move to something, I'm going to say completely different, but sort of fits in with the video that we're making here. And they're called Venn diagrams. Now you may have seen Venn diagrams before, so this may be a little bit of review, but we're going to go over it anyway just to make sure. So a Venn diagram is actually a model that we use for understanding sets, understanding relationships between sets, and understanding operations that you can do on sets. So as a model, in a Venn diagram, the sets are represented as shapes. And if the shapes overlap, the part where they overlap indicates elements that are common to both sets. And then usually, just to be proper about it, we draw some kind of universe set that contains all the sets. So here's our universe set. I'm going to draw that as a rectangle. And I'm going to draw my two smaller sets. That's our universe set, U. And then I'm going to draw my two smaller sets, A and B, as circles. They don't have to be circles and rectangles. They can be literally any shape that you want. Any shape that is useful in helping you understand sets. And then the sets are A and B. And notice that we have this little shaded area in between, in that common area between A and B. That shaded area represents the elements that are both in A and in B. So those elements are in A, those elements are in B as well. And anything outside that shaded area is not going to be in both A and B. They're going to be one or the other, or if they're outside of the circles altogether, they'll be in U but not in A and B. So depending on the problem you're solving or what you're trying to understand about sets, you might want to be flexible in interpreting your Venn diagrams. So for instance, here's our standard picture with two sets A and B. But what if you're in a situation where some of those regions on your Venn diagram don't contain any elements? Well, what you can do if this is useful is put an empty set there to indicate there's nothing there. So what that is telling us is the part of the set B that is not in A does not contain any elements. So there are no elements in B that are not also in A, and that is actually, if you think about it, that's a situation where B is a subset of A. So that's an example of using Venn diagrams to understand sets. I've got a PDF file for you to do some more of that. It's called Cartesian Products and Venn Diagrams, and it's on the PDF file included with this video.